Now let's have a look at different ways of controlling the number of threads when you create threads. So the programming model of OpenMP is that you have a master thread shown in, well, not red, green. And at some points you have parallel regions where you spawn a number of threads. So here is a parallel region, here is another one, and this is a third one. And each parallel region may have different number of threads. So the idea is that you add parallel regions, you add parallelism incrementally until you meet your performance goals, which means that you gradually evolve your sequential program into a parallel program. Okay? Between parallel regions you have sequential parts, and you might even have nested parallel regions, although this is a feature of OpenMP that I really discourage you to use. Since OpenMP 3, there are better ways of dealing with nested parallelism. Rather than creating more threads, you use a concept called tasks, which is part of later lectures. Okay, so there is only one way to create threads in OpenMP, and that's with the parallel construct. Pragma OMP parallel. To create a 4-thread parallel region, you can do that by specifying with a library call OMP set numthreads 4 that the next parallel region will have 4 threads. And then each thread will execute a copy of the code within the structured block. So in this case it means that we get a thread number for each thread. We have 4 threads, so they will be numbered 0 to 3, and poo here will be called 4 times for each thread, and with IDs 0 to 3. Another way of telling the number of threads is by having a clause to the parallel construct itself. This is exactly the same thing as finding out or specifying the number of threads through the library call. Important to understand here is that each thread executes the same code redundantly. So if you want to have the threads to do different things, you can use the ID to make them do different things, or you can use some work sharing construct we will come into later on. Another important thing to understand with parallel regions is that variables that are sort of can be named from within the parallel region, such as the A variable here, which is an array with 1,000 elements. This A will be shared by all threads. So this is a copy. Well, it's not a copy of A. It's a share. There's one copy of A existing. It will be shared. The ID variable, on the other hand, is declared inside the parallel region. And those of you who know how C and C++ works understand that this will be allocated on the stack. And since this stack on each thread is private to the thread, this variable will become private to each thread. And finally, at the end of parallel region, all threads wait until all the other ones have finished. So we have a barrier synchronization, which means that all threads wait here. Now it's time to look at an exercise here. Numerical integration. We have the problem here to calculate the value of pi. Mathematically, we know that this integral is equal to pi. We can approximate the integral as a sum of rectangles, like this. And each rectangle has a width delta x and a height f of x at the middle of the interval, just like this graph here. And this is the sequential code for calculating pi. Relatively simple code, and the more number of steps, the finer the intervals are, and the better approximation of pi you will have. If we look at the sum here, we can see that mathematically you can do the sum in any order. You do not have to do it sequentially from 0 to n, and actually the sum notation here does not specify any particular order, because addition is an associative operation. Now, this means that the loop iteration here should be able to be done in any order. And the only problem we have here is the sum variable, which sort of sums up the global value. What you should do with that, I leave up to as an exercise to you. So we have a exercise here. Create a parallel version of the Pi program using a parallel construct. You should pay close attention to shared versus private variables. For now, the way to privatize variables is to put them inside the stack of a function. You can use these three constructs to control the number of threads, get the thread ID, and to measure the performance of the code here. So get num threads will tell you how many threads you have in the team. Get thread num will tell the thread ID of the currently running thread, and OMP get w time is getting the wall clock time in seconds. So you call this twice and then take the difference to find out. Now go to your computer, write this program, and then come back later to find out what you can do better.